All right, welcome to your first video for AP Stats, Chapter 1, Section 1, something called Categorical Data. All right, so there's two kinds of data that you need to be aware of. The first kind is what we call categorical data. It puts an individual into a category, okay? So when they collect data, this is one type. It could be gender, states, class, like freshman, sophomore, junior, senior, things like that. All kinds of categorical data out there. Now the other type, if you contrast it with it, you'll see the difference, is what we call quantitative variables. This is numerical values that make sense to take averages. For instance, age, height, weight, width of things, all kinds of measurements, anything measurement, time it takes to run a mile, those are quantitative. They're numerical variables that you would take for some kind of study. Now, quantitative variables have to be able to average. Okay, just because it's a number doesn't mean it's quantitative. For instance, a zip code. We don't average zip codes. So a zip code would be considered categorical, or an area code in the same right. Also, like a jersey number, we don't average jersey numbers in sports. We really don't even use them for categorical variables, but we might. That's a possibility. So even though it's numerical, doesn't mean it automatically is quantitative. Stop and ask yourself, can you or should you average them? If you could, then it's quantitative. Otherwise, it's like a category or a categorical variable. Now, important thing to know is that if you can identify the variable as categorical quantitative, that's going to get you really far in this class. Because as we go through this class, you're going to have to identify tests to run, and the test is determined in part by the kind of variable. So it will help you quite a bit on the AP exam if you can identify these really quickly. Now, the next thing you want to know is something called a distribution. The distribution of a variable tells you what values the variable takes on and how often. So it's kind of like a list of all the possible outcomes, if you will. All right, for our first example, pardon if you hear smacking, that's my dog chewing a bone, it's not me. But first example is about some U.S. Census data that we have. So here's a table of data, lots of information in here. You can see it states, number of families, age, gender, marital status, income, travel time to work. So some questions you might see. Who are the individuals in the data set? Who do these people, what does each row represent, basically? Well, each person is a U.S. resident. We know it's U.S. resident because it's from the U.S. Census. So each one is a U.S. resident. You wouldn't just say person, you would be as specific as you can. In this case, we know it's U.S. residents only. So that's why we would say U.S. residents. B, what variables are measured? Identify as categorical or quantitative. So basically, we look at each column and categorizing these, all right? So let's look. Categorical would be state, gender, marital status. All the other ones are numerical, and they would be okay to average. We would average those values. So our categoricals are state, gender, and marital status. Quantitative are the rest: number of family members, age, total income, and travel time to work. And part C, it says describe the individual in the first row. Okay, so what do we know about this U.S. resident in the first row? Well, we know they're from Kentucky. We know they have 2 people in their family. They're 61, they're female, they're married, all the steps. So I'm going to put this in a normal grammatical sentence, all right? The individual in the first row is a 61-year-old female who is married and lives in Kentucky. She has 2 members of her family, a total income of $21,000, and travels 20 minutes to work. So in stats, grammar is important, sentences are important, so don't just list out stuff. If it asks you to describe, you're expected to use regular sentences. Okay, on this slide there's a lot of vocabulary, and that's what we're going to start with, is just a lot of vocabulary. So a data table, what is a data table? Well, it's raw data of each individual. It's not totaled. It's a table, categories, and values, just like we saw in the previous slide. A frequency table, it displays the counts of each variable. So if I wanted to know how many freshmen, it would have a total count of how many freshmen, 15, 20, whatever. But it's a frequency table, how often that one variable occurs. A relative frequency table finds the percent of each variable. So if I had 15 freshmen, I would say that's, 20% of the sample that I took. My table would have percentages on it, and you will see some of that as we go along. But if it has percents, it's automatically relative frequency. So when is it better to use relative frequency? Well, when you want to compare distributions of multiple counts. So let's say you have one sample of males and there's 50, but you were able to sample 150 females. Well, obviously the totals are very different, so the counts are going to look different, but that doesn't mean the answers are all that different. But if you convert them to percents, it would make more sense to compare your data. So if you have different totals in your counts or different totals of populations, you would want to use percentages. What's the most important thing to remember when making a pie chart and a bar graph? And why do statisticians prefer bar graphs? Well, pie charts and bar graphs. Well, proper labeling is extremely important. I'm going to show you some bad examples here in a moment. Statisticians prefer bar graphs because they're easier to compare. Okay? Generally, they're easier to compare and they're less questionable than pie charts. Now, it can be inappropriate to use a pie chart. So look carefully at them if you see them in the media. It says when each percent refers to a different category, that's not a good use of a pie chart, because all the parts of a single whole should end up to adding up to 100%. But if they're different categories, it could end up adding up to more than 100%, and then it's not valid data. It doesn't make any sense. So I'll show you an example in a moment. What are the common ways to make a misleading graph? Like a bar chart. Well, common ways is the vertical axis doesn't start at 0, or maybe the scale on the vertical axis is inappropriate. It doesn't. And there's something called an area principle. I'll show you an example of a graph that violates the area principle in a moment. But your bar, basically it's saying the bars need to be equal in width so that your eyes are not tricked. All right, so here's a first example of a bad chart. This is from COVID in March of 2020 or April of 2020. It was during the pandemic, but note this was in the media. This was actually used, but I want you to notice, look at the x-axis. Okay, that makes some sense. March 18th, they go in order all the way to April 1st. But what doesn't make any sense is the vertical axis. Okay, first of all, there's a problem here because it doesn't start at 0. Your vertical axis always needs to start at 0. All right, and then notice it's going up by 30, by 30, by 10, by 30, by 30, by 30, by 50, yet the width is the same as before, but now it's jumping to 50, by 10, by 50, by 50, by 50. So this is inconsistent in the scaling, and that's going to mess with your eyes. It totally can manipulate the data to say what they want it to say. So know that this was used in a media display, but it's inaccurate because the scaling is really messed up. All right, here is another example of a bad chart used in the media. So this was a pie chart, not the best use of data. However, look at this. See if you can figure out what the problem is here. Allegheny County cases by age. All right, well, hopefully you see that 65%, 5%, that's 70% of the graph. That this section is not 70% of the circle. It's not represented right. And then this is 88%. Well, so many issues. If you add up these percents, it's greater than 100%. That doesn't make sense. And the sections of the graph are not done correctly. And that's because there's got to be some other information in this that they're not reporting. So pie charts, you've got to be careful with it and make sure it's clearly reporting the data. This is not a good example of the use of this data. All right, another bad COVID graph for you. They're trying to show most impacted counties over the past 15 days, a number of cases over time. The table below represents the number of deaths and hospitalizations in each of the impacted counties. So each color is a different county. Okay, great, wonderful. But, and it looks like everything's going down, right? It looks like it's a steady decline, great. But if you look carefully, there is something wrong with the axis. Your vertical axis is fine. It starts at 0 and it looks like it's got good scaling. It's consistent. All right, that's okay, but look at your horizontal axis. Look at the dates. April 28th, then the 27th, then the 29th. First, April 30th, May 4th, May 6th, then May 5th, May 2nd, May... So hopefully, look, this is done out of order. That had to be intentional. There is no way this was non-intentional. It's so out of order, and it's not even making sense how out of order it is. So that had to be done intentionally to manipulate the data to help present some argument they were making that cases were declining, I imagine. That's what they were trying to say. But in order to get that data to look like that, they had to change the x-axis in an inaccurate way. So you just got to be really careful as you look at these cute little graphs they put out in the media. Okay? All right, now, last graph example, bad example for you. Here's one that has to do with Keen sandals. All right, and it talks about where it's searched up, I guess. But what I want you to see here is a violation of what we call the area principle. Okay, notice that it's a nice bar chart. It's great. However, the bars are not equal in width. And so what does that tell us? Well, that messes with our heads because our eyes want to say, oh, Google is winning by far. But that's not always what the data is saying. Okay, but the graphic is saying that, but the data may not. So you have to be careful. Look at the widths of the bars are not consistent. That's a violation of what we call the area principle. So although the length of each sandal corresponds to the correct number, notice there's no axis either to give us a number. The impression that we get is all wrong because we perceive the entire area of the sandal. In fact, only a little more than 50% of all visitors use Google to get to the website. Infographics are notorious for this mistake right here. All right, so look carefully. Look at these things with an educated eye and don't just believe what it's saying. Make sure that the data makes sense. All right, now two-way tables. It is a table that describes the relationship between two categorical variables. So in this situation, its Pew Research Center has asked a random sample of 2,024 adult cell phone users from the US which type of cell phone they own. Here's the results broken down by age category. So now, pause for a second. Notice that the ages are age ranges, not individual ages. Before we said ages were quantitative, but when they adjust them to a range of ages, they become categorical because there's more than one age represented. Okay, so this is considered categorical because they are age in range. And then types of phone, obviously, not quantitative, so they have to be categorical. And so it's a two-way table. We have two categorical variables and the data that relates to them. All right, now, notice we have a total column below and to the right. All right, these totals are what we use to calculate the marginal distribution. Okay, the marginal distribution of one of the categorical variables in a two-way table is the distribution of values of that variable among all the variables described in that table. Now, that's key, all the variables, because you're going to divide by the total of the whole table, because marginal has to do with totals, table totals, basically. Calculate the marginal distribution in percents of type of cell phone. Make a graph to display and describe what you see. Okay, so marginal distributions, we're going to take the totals of each cell phone and divide them by the table totals. So here's my work. For iPhone, the total was 467 out of 2024, giving me approximately 23.1%. Android, 503 divided by the table total gives me 24.9%. And then other would be 1,054 over 2024, 52.1%. All right, so that's finding the marginal distributions of the cell phones. Now, make a graph to display. So this would make a bar chart. So I have my y-axis. I've scaled it, and I've labeled it percents. All right, and then my bar chart. Notice the bars are separate, and I have one bar for each type of phone. And I draw the bar to the appropriate heights. All right, and then describe what you see. It says, I would say iPhone and Android are about the same, but more than half are something else. More than half the people in this table chose another type of phone. That's all I can see from this chart. Can't make any conclusions, I'm just reading the data. All right, same example, but now it's asking us to find a conditional distribution. So definition, conditional distribution of a variable describes the values of that variable among individuals that have a specific value of another variable. Remember, it's not marginal was all the variables, but this is specific of another variable. There's a separate conditional distribution for each value of the other variable. All right, now, you have to decide which condition to base your variables on. And there's something called an explanatory variable and a response variable. We'll cover that way further in the course, but right now you need to know explanatory is what you would consider X, and response is the Y variable. So explanatory is in some ways what you think determines the other, that you could predict the other based on the explanatory variable. So we have to stop and think. If I know the age of someone, does it help me predict the type of phone they might have? Or if I know the type of phone, does it help me predict their age? Which makes more sense? Well, in this case, age probably indicates a cell phone preference more than a cell phone preference indicating an age. So we would say that the age is the explanatory variable. That's the condition we're basing this on, okay? So then it says to calculate the conditional distribution of a cell phone type for the 18 to 24-year-olds. So what I'm going to do is take the total of that column. That's my base for my percentages, okay? And then I do it for each phone. For instance, for iPhone, there's 169 iPhone users out of that age group. So I divide it by that age group's total, and I get 32%. For Android, I take 214 and divide it by that age group's total. And then for others, 134 divided by 517, and I get the percentages. Notice, I'm still doing percentages, but what's changed is that I'm taking the total of one category for each phone. That's how it's a conditional is different than the marginal. The marginal takes the table row totals divided by table totals. Conditional would probably take a column total divided by table totals. If the columns are your explanatory variables, that could change. Okay, so the way we display categorical data like this is called a segmented bar chart, or maybe you could call it a stacked bar chart, but usually segmented is what we say. So to create a segmented bar chart, we find the conditional distribution for each of the explanatory variables. Okay, so when we want to display the relationship between two categorical variables, we use what's called a segmented bar chart. All right, so here's your steps for creating it. I'm going to walk you through it. It says first find the conditional distribution for each of the explanatory variables, which is what we did in the previous slide. We did it for one of the explanatory variables of the 18 to 24-year-old age group. So I just copied our data right here, our conditions that we found. But we're going to do it for each of the age groups, okay? So here's the definition, displays the relationship between two categorical variables. So the next thing I'm showing you is I've done the same thing, the conditional distribution for the other two age groups. Okay, we walked it through for the 18 to 24-year-olds. Here's the other two age groups and their corresponding percentages. Now, the next thing I would need to do is create a bar chart with one bar for each explanatory variable. And I would label the y-axis as relative frequency, drawing each bar to the 100% mark. So notice each bar is an age group. I've labeled it. They all are the same height, so they'll go up to 100%. And then I shade them different colors for each of the response variables, which in this case is phone type. And notice it has a key. The blue is the other phone, the red is the Android, and the pink is the iPhone. Now, how we break this up is based on our percentages. So look at the 18 to 34-year-old bar. Okay, the first percentage for iPhone was 32.7, so I would mark it at brown 32.7 and shade it pink, since pink is iPhone. Then I would stack 41.4 on top of that. That would take the total up to what, like 74% roughly. So I would mark it around 74 and shade it for Android. And the remaining percent should be about 25.9% if I've done it correctly. Same thing with the next age group. iPhone is 26.8%, so that's about there. Android's 29.7%, so it's a little bit bigger. That takes us up to 55%-ish, okay? And then the other is the 43%. And the same process again for the 55 plus group. But they're based on the conditional probabilities. So you have one bar for each of the explanatory variables, and you find the corresponding percentages. That's how you build your segmented bar graph. Now, what do we do with this? Well, we analyze these bar charts to, or segmented bar charts, to see if there's an association between the two variables. So we say that there is an association between two variables if knowing the value of one variable helps predict the value of another. If knowing the value of one variable does not help you predict the value of other, we say there is no association. It's that simple. Now, how can you tell by looking at the graph? Well, you're looking at the segments. Do they segment in the same places, or are they different? Okay, if the segments look the same, then there's no association. If they're different, like in this example, definitely different areas of the different color, that means there is some kind of association. We're not saying cause and effect. We're just saying there's some kind of association there. So, looking at part A, it says, explain what it would mean if there was no association between age and cell phone type. Well, that would mean that knowing the age of the person does not tell us anything about what kind of phone they prefer or might prefer. Now, based on this data and based on the segmented bar chart, it looks like there is something there. So based on this, can we conclude there's an association and justify? So I would say, based on this data, 18 to 34 and 35 to 53-year-olds, or 54-year-olds, it should be. Based on this data, 18 to 34-year-olds and 35 to 54-year-old age groups prefer iPhone and Androids because more than 50% of each of these age groups own these. So notice that iPhone and Androids, that's more than 50% of both of those age groups. Now, it's not that way with the other. Much less than 50% of the 55 plus age prefer the iPhone. So that tells me that there's an association. And so when you see that there's an association, you don't just say yes, there's association, or no, there's not. If it's a yes, then you need to give specifics and give some percentages based on your segmented bar chart, making comparisons between the explanatory variables like I've done here. All right, so this concludes the first video for this chapter. Hope you enjoyed it, and we'll see you in class.